I must speak about the Dirichlet problem in the space of continuous function. What is problem? The problem that in space of continuous function, Cauchy type integral is not invariant. Therefore, after very first works, for example, Fatou work which solve Dirichlet problem in this disk, after great books, Muskhelishvili and Gakhov, singular integral operator, everything, all investigation returned to Hölder space and LP spaces, where Cauchy type integral is good, because images such the spaces in the same type of spaces. Now, about the problem which we will consider. We consider first this 2n order equation, only 2n order derivative we have, and we suppose that this equation is properly elliptic. Therefore, if you consider the characteristic equation, which is equal to 0, we have n roots of this equation in the upper half plane and n in the lower half plane. We are looking for a solution u of the equation 1 in the class. The main novelty of this foundation of this posing is following, that we consider that the function n-1 order derivative continues up to the boundary. Inside it will be 2n differentiable, but we know that the solution inside will be analytic. Therefore, this condition is not necessary, but this is important. We consider Dirichlet problem. So Dirichlet condition is in the following way, where fk functions are given functions from the class Cn-1 minus g gamma. So continuous with n-1 minus g derivative up to the boundary. Now, two words. If the solution u belongs to the class Hölder continuous, so n-1 derivative belongs to Hölder class, and given boundary function in the Hölder class, n minus k minus g alpha, in this problem is studied in many works. I briefly say 2 words about the history of the question. First of all, the problem 1.4 is Fredholmian. It's the general result. It's very known result. It's written in Lyon's Maginus. In Thomasyan's book, it proved in another way. But in all cases, this is a classical result. The problem is following. We want to define necessary sufficient unique solvability condition and the defect numbers of the problem. Defect number, what I mean by defect numbers. This is a number of linearly independent solution of homogeneous problem when fk are 0, and necessary linearly independent necessary sufficient conditions to the fk for the solvability of inhomogeneous problem. This is, I denote defect numbers. In some cases, definition differs from this. We say some result. The first in the paper, Thomasyan, 1090 1969, he, in differential equation, this paper, it was done complete research of the Dirichlet problem for the system of second-order elliptic equation with constant coefficients and in elliptic domains. The defect numbers was defined and in explicit form, and the condition of the solvability of an homogeneous problem were defined. The difference between weakly and strongly connected elliptic system was found. The defect numbers are finite, and the problem is Fredholmian for weakly connected system, and it's neither Fredholmian nor Noetherian for strongly connected system. In our formulation, we suppose that the number of the complex roots is the same in upper and lower half space. This is connected with weakly and strongly connected connectiveness. Weakly connected system for second order if the two roots belongs to the same half plane, and weakly connected if in different half planes. For second order improperly elliptic equation, elliptic, this is connected with strongly connected system second order. For n equal 1, so the second order, the roots of equation satisfy this condition. In 68 year, Tovmasyan completely studied this problem. And the functional where mentioned the functional class where problem is Noetherian. This class of function will be analytic function inside unit disk. So it is necessary to continue this the boundary function inside unit disk. So, the formula of the general solution of the equation was helpful to resolve this problem in the unit disk. For n equal to fourth order equation, necessary sufficient condition for the unique solvability were found in my work 1999 and Burichenko in 2000 year. Analogous result for how order equation, but if the characteristic equation too has only simple roots, so multiplicity is 1. This was found in my work, in Tovmasyan work, 2002, and in the work of Bursky-Burichenko, 2005 year. The case when the multiplicity of the roots of equation is not more than 2, the problem was considered in the work of Iritian in 2003. He was aspirant of postgraduate pupil of Tovmasyan. And if the unique solvability, this result will be considered in only if multiplicity is equal to. And after that, in 203 year, was found the representation of general solution of equation, which helps to solve the problem for arbitrary multiplicity of the roots of characteristic equation. The same, along with the investigation of elliptic equation, There are many papers, not many. So the paper of Alexandrian, John, Borgen and Dauphin, which connected with Dirichlet problem for hyperbolic equation. In Alexandrian work, it was done for the circle. John considers arbitrary domain, but the equation was u x y equals 0. He considers arbitrary domain and the unique solvability of the Dirichlet problem connected with the geometry of the boundaries. So he considers two images along with y-axis and x-axis. So characteristic of this equation, and this maps here. And if this, we can say billiard is dense on the boundary, in this case, the Dirichlet problem has a unique solution. So the same result what given in this work. What? Carambol. Carambol. So this way. Further, we must mention the work of Bursky, where he considered Dirichlet problem for arbitrary kind of equation. So it may be elliptic, may be non-elliptic, and so on. And he considered only homogeneous problem. And this was this duality equation, domain duality relation. In this case is following. So boundary values for homogeneous problem, it means that 1 minus x power 2n equal Lx is the differential operator which we have. The same, this is connected, so this equals 0 if and only if delta plus 1 and Lxc Vxc equals 0. This duality helps him to solve the homogeneous problem. And this some result about this equation, but everything which is considered here deal with Hölder spaces. For the continuous function, we can say there are a few works. We must mention, of course, the very interesting article by Nevanlina, 925, where he considers Dirichlet problem in the half space with arbitrary continuous data. He, after that, approximately the same kind of the work was written by Thomasyan in 61, but he considers only polynomial growth in infinity. But idea almost the same. Of course, he didn't know about Nevanlina work. We know about it maybe 10 years ago, not earlier. And after that, in this work, in 207 work, we write with Thomasyan the second order elliptic operator in the class of consider continuous function. And after that, Soldatov in 2009 find the very good kernel which works in the space of continuous function. All these works, Nevanlina, Tovmasyan, Soldatov, and this one, connected with the construction of special kind of kernel, which used instead of Cauchy kernel. But Professor Hayrapetyyan introduced new formulation of boundary value problem, mean convergence boundary conditions. Maybe I will show what kind of this one. Yes, he replaced the boundary conditions in a classical way by this one. So norm derivative minus phi k radial limits is equal 0. And this helps him to solve this problem in many classes of the boundary functions. Now the main result which we get following. Now, in Hayrapetyyan works and his people works, he considered only model higher order equation, B-analytic, polyanalytic, and so on. Now, for exact formulation of the main result, we need following notation. First of all, using this complex differentiation operator, we can transform the equation to this form. Here, mu g and mu g are constructed using lambda g roots of characteristic equation. If lambda belongs to upper half plane, we get this one, and if lower half plane, mu g will be so. So mu g and mu g both less than 1 by modulus. After that, from the we replace boundary condition by equivalent conditions. So n minus 1 derivative by z, the conjugate and z, and additional condition which helps us to get the previous function using differentiation. Now, here fk will be simply continuous function determined uniquely by the boundary function fk. Therefore, the problem 1,4 equivalent to 5,6. Now, the result is following. We define following vectors. Vectors are following. By using mu, you get C is a binomial coefficient. C, S, S, S varied from 0 till multiplicity minus 1. Multiplicity of the mu g, which connected this AG and BG. Using this vector, we construct n matrices. A connected from A vectors and B from B vectors. M is a Jordan form, so GQ1 mu1 is a Jordan block of this equation, and L the same Jordan blocks with this one. Well, maybe I show. So, theorem is following, which is proved here. The problem 1,4 is uniquely solvable if and only if these matrices are non-singular for n from n plus 1 till infinity. Delta n so is not equal 0. If the condition fails, for example, if delta L0 is equal 0, then the solution, homogeneous problem, has a non-zero solution, which is a polynomial of this order. And corresponding non-homogeneous problem has a solution if the boundary function satisfies one linearly independent condition. Maybe I will see the case. For example, if you consider n equals 0, and we consider only simple roots. In this case, the A matrix is 1 mu 1, 1 mu 2. B is the same, 1 mu 1, and so on. In this case, M and L will be simply diagonal matrices, which we have. And you see that if K is 0 or 1, in this case, this matrix is singular because determinant is equal 0. But it's not reduced to non-uniqueness of the homogeneous problem solution. If K is equal to, it will be simple van der Monde determinant, which is different from 0 because mu 1, mu 2, mu 1, mu 2 are different. Therefore, it's not equal 0 for arbitrary in all cases. But if K is greater than 2, this matrix may have may be singular. So determinant may be equal 0. Now, what Так. By our assumption on mu and nu, we have that they are less than 1. Therefore, if n tends to infinity, this determinant delta n tends to determinant A multiplied determinant B, which is not equal 0 for B. Therefore, the condition 10 is valid for sufficiently large n. So we can say that defect number is finite. If the boundary function belonged to this class, this result was obtained in 203 work. For continuous function, we use Abel summation of the Fourier series. So instead of, we consider following. So instead of what is? So if you have continuous function, the Fourier series may not converge to this function. But if you consider such dk Rk, this converges to continuous function uniformly for R equal 1. I mentioned Hardy-Rogozinski because it's very good book. So it's known result. So if we consider maybe I say 2 words about proof. So if how much time I have?
You have almost
5?
6 minutes.
6 minutes. Very well. So I say 2 words about the proof. So if you consider second order equation, the equation is following, and continuous function will be this one. So the general solution, this one, and Dirichlet condition has following form. Using lemma of Thomasyan, we can represent by the function which analytic in the unit disk, therefore is expanded by Fourier series, and substituting this this expansion in boundary condition, we get following equation for the Fourier series, and we can equate this coefficient for corresponding powers of z and z conjugate. Therefore, instead of fk, if we consider continuous function, we get simply r power k fk, r power modulus k f minus k. And using that delta k not tends to 0, therefore you get the coefficients from the continuous function up to the boundary. So we get that. Now, 2 words about open problems. First problem is following. We consider such determinants. We see M and L has norm which is less than 1. Therefore, if G tends to infinity, this part tends to 0. S is non-singular. But problem is following. Can we prove that if delta M equals 0 for some M, then for greater G, it will be not equal 0. In some sense, it will be less for G great values. Therefore, maybe it will be the case. I cannot prove it, but in all cases which we consider, we have it. And next one is following. We see that defect numbers of the problem are determined by the formula, this one. We know that if L is sufficiently big, then rank will be equal to n. So in this sum, we have only a finite number of summands. But how much? For n equal 0, we know that second order equation has only unique solution. For n equal 1, in known cases, in all known cases, the number may be equal 0 and 1 only. So the supposition that in general, maybe defect numbers of the problem at most may be equal to n. So it's open problem, I don't know about it. So that's all which I must say. Maybe
Then you can thank
yes, I think that's